In the vast expanse of space, where billions of stars dance in the endless void, an extraordinary and colossal event unfolds: the formation of planets. Imagine how, in this silent light of the stars, clouds of gas and dust slowly but inexorably gather, giving birth to stellar systems. This process, which seems eternal to human eyes, spans billions of years. Yet for the cosmos itself, it is but a fleeting moment. Consider this from a temporal perspective. If 1 year in Earth's history were equivalent to 1 day, the process of planet formation would stretch into eternity. Within these immense clouds, composed of hydrogen, helium, and other elements, a tumultuous movement begins. Gravity, like a mighty conductor, orchestrates this chaos, drawing particles together to form the core of a future planet. Over countless millions of years, these cores grow, accumulating more material and gradually forming masses that become increasingly stable. Picture these burgeoning clumps of matter spinning, giving birth not only to planets, but also to moons, comets, and asteroids. Each element we find on Earth was once part of this cosmic ballet, where stars and planets, like musicians in an orchestra, play their roles in a symphony we can barely comprehend. In the depths of the cosmos, a new world is born, not just of rocks and metals, but of entire planets where life will later unfold. There is something mystical about this silent and majestic process, making us ponder our place in this boundless universe. We explore not only the physical forms, but also the time encapsulated in every mineral fragment, every drop of water. As we gaze at the stars, we are not merely observers, but participants in this grand cosmic process. We stand on the threshold of discovery, as if we ourselves are involved in the creation of a new planet, much like the one we inhabit. Each planet, each moon, and each asteroid carries its own history, which begins in the boundless void. This history is filled with mysteries and revelations that await us in the depths of the cosmos. In this context, our journey of studying Earth and its formation is but a part of a broader picture that we are yet to unravel. Time, as an unyielding teacher, reveals its secrets to us, and we are just beginning to grasp the magnitude of our place in this boundless existence. In this cosmic journey, filled with wonders and discoveries, we are but a tiny spark in the great fire of existence. From the surrounding space composed of gas and dust, the formation of a protoplanetary disk around a young sun began approximately 4.5 billion years ago. A vast cloud, primarily consisting of hydrogen and helium, began to rotate under the influence of gravity, and its rotational speed increased as the cloud contracted. As a result, the temperature in the center of the cloud rose to thousands of degrees Celsius, initiating thermonuclear reactions. The energy released by these reactions created a brilliant glow that contrasted with the darkness of space. Dust and gas particles began to condense, forming a disk several million kilometers wide. Within this disk, matter rotating at different speeds collided and combined, creating a magnificent cosmic dance of matter. The smallest particles, intertwining to form larger objects, became planetesimals, which then coalesced to form protoplanets. The formation of this disk also led to the emergence of various temperature gradients, where high temperatures prevailed near the Sun, and on more distant distances, icy comets and gas giants formed. This process lasted for millions of years, and during this time, the disk gradually evolved, forming the system in which we live today. The brightness of the disk, combined with the vast black expanses of space, created a spectacle that captivated the minds of ancient astronomers and contemporary scientists. At this stage of cosmic evolution, each particle played a unique role in the formation of future planets, moons, and other celestial bodies that ultimately filled our solar system. During the formation of the protoplanetary disk, a significant amount of heat was also released, allowing particles to remain in motion and not settle on the surface. This imbalance in the distribution of energy and matter created conditions for the subsequent formation of complex structures such as planets, asteroids, and comets. For example, at a distance of about 3 astronomical units from the Sun, where the temperature was lower, icy bodies began to form, which later became the basis for the creation of gas giants like Jupiter and Saturn. This cosmic process, filled with slow but inevitable movement of matter, became the foundation for everything we know about our solar system. The study of the accretion process is a dive into a slow and majestic dance of cosmic particles that unfolds over millions of years. Accretion begins with microscopic dust grains, composed of various elements and compounds, colliding with each other in the vacuum of space. These collisions, though occurring at high speeds, appear to slow down when observed on the scale of cosmic time. Grains with mass start to stick together under the influence of gravity and electrostatic forces. For instance, the collision of two dust grains can result in the formation of a tiny pebble just a few millimeters in size. This process repeats as the formed pebbles attract other dust grains, increasing their size. Through this continuous process of merging, over millions of years, larger bodies such as asteroids and planetesimals, which can reach several kilometers in diameter, are formed. Imagine if we could observe this long and almost hypnotic process. In the vast expanse of the universe, billions of particles slowly rotate and collide, creating sparks when they combine and forming new matter. This movement resembles the smooth and slow spiraling of a vortex, where each new particle contributes to the formation of a larger object. Time here seems almost infinite, and although the accretion process takes millions of years, each collision is a moment of creation that brings us closer to the formation of a complete planet. It is interesting that in this chain of events, even the smallest particles, such as cosmic dust, play a key role and can become the basis for the formation of giant planets. When a planet finally forms at the end of this process, it begins to interact with its surroundings, attracting other objects and becoming part of a dynamic system that could one day be part of a solar system. This accretion process serves as the foundation for the formation not only of planets, but also of other celestial bodies such as moons and comets, which also arise from the slow and relentless work of gravity. During the formation of planetesimals, which are the first large bodies in the protoplanetary disk, reaching sizes of kilometers, gravity begins to play an increasingly significant role. These primary objects, composed of rocky material, start to attract surrounding material, forming larger and larger accumulations. When the diameter of planetesimals reaches around 100 meters, their gravitational attraction becomes sufficient to gather more and more particles around them, leading to the formation of numerous solid bodies that orbit like cosmic wheels spinning in the vast expanse. Imagine the cosmos filled with thousands of such rocky bodies, each unique. Some are covered in a layer of dust and meteorites. Others sparkle with metallic inclusions reminiscent of stars in the night sky. Against this backdrop of motionless emptiness, where comets occasionally streak by with their tails, planetesimals stand out as oases of solidity and stability. Gravity, acting like an invisible hand, relentlessly draws already formed bodies towards their centers, thus providing the foundation for the formation of planets. These objects, starting as small pebbles, gradually grow to sizes that can be considered full-fledged planets. During this time, in the protoplanetary disk, constant collisions between planetesimals occur, which can result in the formation of larger objects, such as protoplanets. This process, which began around 4 billion years ago, became the cornerstone for the formation of the solar system as we know it today. With each new formation of planetesimals, conditions were created for further changes, and each of these bodies played a role in the grand game that ultimately led to the creation of planets, including our Earth. At this stage in the cosmos, one could already observe the formation of the first large bodies that would later become the basis for the planets inhabiting our solar system. From a multitude of small planetesimals composed of dust, ice, and rocks, the proto-Earth gradually formed, a process that can be compared to the slow but steady awakening of a colossal organism. Over millions of years, under the influence of gravitational forces, these tiny particles began to collide and coalesce. Each encounter gave birth to new bodies that, in turn, became larger. This was akin to how water droplets accumulate to form a stream, which then becomes a river. As a result of these aggregations, increasingly massive objects emerged, which, like pieces of a mosaic, joined together to create a more complex structure. At this stage, the cosmos was filled with a remarkable order. Each element found its place in this grand design. Gradually, under the heat generated by collisions and radiation from surrounding stars, differentiation processes began, with heavier elements such as iron sinking to the center, while lighter ones like silicon and oxygen rose to the surface. This differentiation led to the proto-Earth acquiring its initial layers: core, mantle, and crust. In this context, not only the planet itself, but also its atmosphere, composed of hydrogen and helium, which were gradually displaced by heavier gases such as carbon dioxide and water vapor, was formed. Time passed, and from chaos, forms emerged that would later become the foundation for life. The proto-Earth, surrounded by clouds of dust and gas, increasingly resembled the planet we know today. But it still had a long way to go before reaching full maturity. This process of formation, like the universe itself, was slow and inexorable, spending its millions of years in the silence of space, creating conditions for life to one day appear on this young planet. As a result of these long processes, a solid surface eventually formed, which became the basis for future oceans and continents, as well as for the life that would appear billions of years later. In the early stages of Earth's formation, approximately 4.5 billion years ago, one of the most significant events in the history of our planet occurred: the hypothetical giant collision with the protoplanet Theia. This giant planet, roughly the size of Mars, was slowly approaching Earth on its orbit. The process of approaching the two planetary bodies took millions of years, during which they crossed each other's orbital paths, creating a spectacular cosmic dance. Finally, the inevitable moment of collision arrived. This was not just destruction, but a majestic cosmic event in which the collision of two massive bodies released a colossal amount of energy. Upon impact, the temperature on the surface reached thousands of degrees Celsius, and at that moment, molten rocks and gas were ejected into space at incredible speeds. Fragments of Earth and Theia were scattered in space, forming a cloud of molten material that later became the basis for the Moon. This cloud, consisting of metallic and silicate particles, orbited around Earth, forming an accretion disk where complex processes of cooling and condensation took place. As a result, massive waves of molten material, formed due to the collision, created a new landscape that later became the basis for the formation of the Moon. Scientific models show that as a result of this cataclysm, numerous fragments were created in space, some of which became moons of other planets, while others returned to Earth, adding additional elements to its composition. Scientists such as Christopher Kahn and his colleagues from the University of Texas studied the isotopic composition of Earth and lunar rocks, confirming this hypothesis. They found that the isotopes of oxygen found on both Earth and the Moon are practically identical, indicating a common origin. This hypothesis of a giant collision not only explains the formation of the Moon, but also reveals the complex processes that occurred in the early solar system when planets were still forming and changing under the influence of gravitational interactions and collisions. The entire process became the basis for understanding how Earth acquired its current structure and atmosphere, which laid the foundation for the emergence of life on the planet. From the debris ejected in the aftermath of a colossal collision between young Earth and a Mars-sized planet known as Theia, the Moon began to form. This catastrophic impact, which occurred around 14 billion years ago, left behind a vast amount of material that began to orbit around Earth. Over time, the ejected particles, composed of rocks and metals, gradually coalesced into an accretion disk, where particles collided, increasing their mass and gravitational attraction. This process did not happen instantaneously. Millions of years were needed for the small fragments to start combining, forming larger bodies. Gradually, these bodies grew to several kilometers in diameter and coalesced into a single entity, eventually forming the Moon we know today. In this chaotic cosmic environment, a grand process of creating a new celestial body unfolded. Particles collided, adhered to one another, and through gravity, larger objects formed, continuing to orbit the young Earth. The satellite grew, reaching sizes where its gravity began to influence the surrounding environment. This process was not only slow, but also remarkably harmonious, creating a sense of calm and order amidst the cosmic chaos. Approximately 30 million years after the collision, the Moon reached its final size and began to exert an influence on Earth, regulating its axial tilt and, consequently, its climate. Currently, the Moon is located approximately 380,000 kilometers from Earth and continues to have a significant impact on ocean tides and many other natural phenomena. After the formation of Earth, approximately 14 billion years ago, the planet was a completely molten sphere of magma, heated to unimaginable temperatures exceeding 1,000 degrees Celsius. Its surface bore no mountains or seas, only an endless ocean of fire, radiating a brilliant glow. Waves of liquid rock, resembling an ocean, rose and fell, creating the impression of endless motion. In this hellish landscape, there were no familiar landscape elements, no green vegetation, no sky, only dark clouds of toxic gases rising from the molten minerals and forming a dense atmosphere devoid of oxygen. This was a world where even the air, filled with harmful elements, did not permit any form of life. The temperature conditions were so extreme that no molecule of water could remain in a liquid state, and even if any forms of life had emerged, they would not have been able to survive in such conditions. Periodically, streams of magma erupted onto the surface, forming craters and domes, but due to the constant heating and activity, these formations quickly disintegrated. Earth at that time was in a state of constant transformation, where each moment could bring new forms of relief and structures created by powerful volcanic eruptions. This fiery sphere, surrounded by clouds of poisonous gases, was the precursor to our planet, which, after millions of years, would begin to cool and form more stable conditions for future life. At this stage of formation, Earth's structure remained dynamic, with an ongoing struggle between internal forces creating new continents and external influences that could potentially alter its fate. This period was just the beginning of a long journey towards the creation of the surface we know today, where oceans and continents would eventually appear, along with all life. It is important to understand that at this time, there were no signs of civilization or even the simplest forms of life, as the conditions were completely unsuitable for their emergence. Studying early Earth, it is impossible not to imagine a magma ocean that filled the planet's surface. At that time, about 4 billion years ago, the planet was a churning, glowing mass of molten rock, with temperatures reaching 800 degrees Celsius. In this ocean of magma, constant movements occurred. Waves of hot material rose and fell, creating a spectacle reminiscent of ocean waves, but instead of water, it was bright red, glowing liquid. Vortices of molten rocks and sparkling particles rose into the air, while eruptions of even hotter material from Earth's depths spewed plumes of ash and gas that could rise kilometers high. The surface temperature was so high that even spilled magma, upon contact with air, instantly turned into clouds of steam and gas, forming a dense atmosphere. The colors of the hot material varied from bright yellow when the magma was in full motion to deep red as it cooled and began to solidify. This was a time when Earth was in a state of constant change, and every square meter of its surface could hide new mysteries waiting to be discovered. These conditions were not only extreme, but also unique, as it was during this period that the first minerals formed, which later became the basis for the creation of rock formations. Against this fiery backdrop, one could observe numerous chemical reactions occurring in water saturated with dissolved minerals, which eventually led to the formation of early oceans and continents. Physical processes such as convection in the mantle contributed to the constant movement of magma and the formation of new crustal areas, which later became the foundation for all Earth's life. At that time, there was no living organism on Earth, as the conditions were too harsh for any form of life. But it was this magma ocean that served as the starting point for the further development of our planet, laying the foundations for future continents and oceans that would form over millions of years. Scientific research of this period shows that magma processes played a key role in the formation of plate tectonics and the creation of volcanoes, which, in turn, became important elements in the development of ecosystems at later stages. The process of differentiation of Earth's material, which occurred during the early stages of our planet's formation, is one of the most significant events in the geological history of Earth. This process began approximately 200 million years after the formation of Earth, when the planet was still in a molten state. Heavier elements, such as iron and nickel, began to slowly sink towards the center of the planet under the influence of gravity, forming the core. These elements, with their high density, gradually displaced lighter substances, such as silicon and oxygen, which rose to the surface. This process resembled a slow but inexorable dance of matter, where each element found its place in the complex internal structure of Earth. Research shows that differentiation occurred over millions of years, resulting in the formation of a multi-layered structure consisting of a core, mantle, and crust. The core, primarily composed of iron and nickel, has a radius of around 1,300 kilometers and is divided into an inner and outer core. The inner core is a solid sphere that, according to theory, formed due to the high pressure exceeding 1 billion atmospheres. The outer core, on the other hand, remains in a liquid state, creating conditions for the generation of Earth's magnetic field through the process of convection. The mantle surrounding the core extends more than 2,000 kilometers and consists of silicate minerals rich in magnesium and iron. It also contains convective flows that cause the movement of tectonic plates on the surface. These flows are formed due to temperature gradients within the mantle, where hot masses rise and cooler ones sink. This process not only influences geological activity, but also the climatic conditions on the planet's surface. As a result of differentiation, a clear boundary was established between the upper and lower mantle, as well as between the mantle and the crust. Earth's crust consists of lighter silicates such as quartz and feldspar, and has a thickness ranging from 5 to 40 kilometers. This crust, formed as a result of the cooling of the upper layers of the mantle, is the layer on which we live. Thus, the process of differentiation not only created Earth's internal structure, but also became the basis for the emergence of life, as it was the complex composition and distribution of elements that allowed various ecosystems to form on the surface. This process continued over millions of years, gradually creating conditions for the formation of continents and oceans that we observe today. Differentiation is a fundamental process that determined not only the geological structure of the planet, but also its ability to support life. In this regard, it is important to note that modern methods of study, such as seismology, allow scientists to gain a deeper understanding of the internal processes of Earth and their influence on its surface. The iron core of the Earth formed during the planet's accretion process, which began approximately 4.5 billion years ago. At that time, when the Earth was still hot and molten, heavy metals such as iron and nickel began to accumulate in its center due to gravitational attraction. This process was similar to how drops of mercury coalesce into a single large drop, forming a dense metallic heart of our world. As a result, a massive sphere of molten metal formed in the center of our planet, which, pulsating, created conditions for the subsequent formation of more complex geological structures. Scientists suggest that as this sphere cooled, a process of crystallization began, resulting in the formation of iron crystals that gradually became the basis for further development of the core. Research using seismic data shows that the inner core of the Earth reaches temperatures of around 5,000 degrees Celsius, comparable to the surface temperature of the Sun. Such a high level of heat is maintained due to the radioactive decay of elements and the pressure created by the layers of the Earth. The complexity of this structure underscores the importance of its study, and it is here that we should mention that the formation of the iron core was a key stage in the development of the planet. It became the foundation for the future formation of the Earth's magnetic field, which protects us from solar radiation and cosmic particles, although we will discuss the magnetic field later. This process of core formation also illustrates how geological processes can influence life on the surface. For example, moving masses of metal in the core create convection currents that can affect plate tectonics and volcanic activity. It is important to note that without this dense metallic core, life on Earth could have looked very different, and the climate and atmosphere would have been subject to much harsher conditions. Research using seismology shows that the Earth's core is not homogeneous and has a complex structure consisting of various layers, each playing its role in the dynamics of the planet. The cooling of Earth's surface began approximately several million years after its formation, when the planet was filled with molten magma, resembling a boiling ocean. At that time, the surface temperature reached several thousand degrees Celsius, and it was only over time, as Earth gradually lost heat, that this initial magma mass began to cool. Imagine a hot drink in a cup, which cools down a bit with each second, and so the surface layer of Earth began to form a thin but fragile crust. This crust, the first Earth's crust, was formed under constant catastrophic events, volcanic eruptions and powerful earthquakes, which brought thick layers of magma to the surface, creating new formations. Scientists note that already 30 million years after the planet's formation, about 4 billion years ago, this crust became sufficiently solid to support life on it. However, despite its apparent stability, this crust was extremely vulnerable. It was constantly being destroyed by external factors, erosion, water, and wind impacts, as well as internal processes such as plate tectonics, which disrupted and raised parts of the crust, creating mountain ranges and faults. This constant destruction and restoration created a fragile balance, which, like a hot drink, could be disrupted at any moment. Periods of stability in Earth's history alternated with catastrophic events, such as the formation of supercontinents, which occurred every few 100 million years. These supercontinents, like Pangaea, existed as a result of the union of continents and were ultimately destroyed by their breakup, which also contributed to climate change and living conditions. In this context, it is worth noting that about 200 million years ago, Pangaea began to break up, leading to the creation of the Atlantic Ocean and the change in the global ecosystem. This cooling and crust formation process was not simple. It involved many factors, such as pressure, temperature, and magma composition, which influenced how the first continents were formed and destroyed. The crust formed as a result of these processes became the basis for further geological activity and the formation of diverse ecosystems on Earth. It is currently known that the age of the oldest rock found on Earth exceeds 4 billion years, indicating that the crust formation process was not only complex, but also long-lasting. The first solid crust of the Earth formed approximately 3,800 million years ago, when the planet was still in an active stage of geological development. This primary surface had a dark basaltic color and was a constant target for volcanic activity. Imagine a planet where a thin, solid shell, composed of black magma, floated on an ocean of molten rocks. Beneath this crust, which was as fragile and unstable as the crust on hot chocolate, lay powerful streams of molten magma, eager to break through to the surface. During volcanic eruptions, streams of red-hot magma would burst forth from the Earth's depths, creating bright fractures and craters that stood out against the dark, solidified rock. These fractures, like wounds on the planet's body, glowed in bright orange and red hues, indicating that the Earth's interior was active and alive. The volcanic activity was so intense that even small eruptions could spew tons of ash and gases into the atmosphere, affecting the climate and composition of the atmosphere at that time. Geologists note that this primary crust was not uniform. Areas of solidified rock alternated with younger volcanic structures, created by frequent eruptions. Some of these areas cooled, forming lava plateaus, while others remained under the influence of high temperatures and pressure, facilitating the formation of new minerals. Scientists such as Dr. Christopher Johnson from the Institute of Geology assert that this crust served as the foundation for the formation of more complex geological structures that appeared later, as continents began to slowly drift and merge. Essentially, this primary crust was the beginning of what we now call continental crust, and it played a crucial role in the formation of the first ecosystems on Earth. Volcanic activity also contributed to the formation of the first atmospheric conditions, which could have influenced the development of life. Approximately millions of years later, as the crust became thicker and stronger, continents began to form from these basaltic masses, creating the foundation for the modern Earth's landscape. Numerous studies show that this early crust was a significant object of study for geologists, allowing them to understand how the processes of Earth's formation occurred and how they influenced the further development of the planet. On the nascent crust of Earth during the early geological epochs, there was intense volcanic activity, creating a spectacle that is hard to imagine. Thousands of volcanoes, including giants like Mount Kilimanjaro, erupted streams of molten lava, covering the planet's surface with layers of magma and ash. These eruptions were constant, with one volcano dying down, while another began to spew powerful fountains of magma, reaching heights of several kilometers. Volcanic gases such as sulfur dioxide and water vapor filled the atmosphere, forming thick clouds that were later transformed into acid rain, influencing climatic conditions. Rivers of lava flowed down the slopes of volcanoes, filling depressions and creating new landscapes, with temperatures of these flows sometimes exceeding 1,000 degrees Celsius. This process occurred amidst the constant movement of tectonic plates, which collided and diverged, contributing to the formation of new volcanoes. Geologists like Dr. Emily Watson from Cambridge University note how this volcanic activity shaped continents and oceans, creating conditions for further life development. The continuity of volcanic activity at that time was such that at any moment one could see the glow of eruptions reflected in the atmosphere, inspiring poets and artists. This wild and restless world, filled with power and energy, became the foundation for the formation of soil that later allowed the development of diverse ecosystems. It is important to note that at that time, Earth was virtually lifeless, and only due to this active process were mineral resources formed, which later became the basis for life. Scientific research shows that the volcanic activity of that time was 100 times more intense than in the last millions of years, making this period unique in the history of our planet. A volcanic eruption similar to the one that occurred on the island of Krakatoa in 1883 only underscores the scale of the destructive power that was characteristic of early Earth. Early Earth's atmosphere was a dense and opaque blanket of gases that enveloped the planet, creating conditions vastly different from those we know today. This atmosphere was heavy, toxic, and rich in substances that prevented sunlight from freely reaching the surface. The gases that formed this primordial envelope were released from Earth's interior through intense volcanic activity, which was characteristic of the Archean era, approximately 4 to 2.5 billion years ago. During this time, catastrophic volcanic eruptions spewed vast amounts of vapors and gases, such as water vapor and carbon dioxide, into the atmosphere, creating the first breathable environment for Earth. Imagine the clouds of ash that formed from these eruptions, which then obscured the sky, creating a dark and oppressive atmosphere. This environment was extremely hostile to the life we know, with high temperatures and unbearable conditions. Scientists like Dr. Ian Platt from the University of London note that it was during this period that conditions were established that later became the foundation for the emergence of life. Despite its toxicity, such an atmosphere played a crucial role in the planet's further development, as these gases provided the conditions for chemical reactions that ultimately led to the appearance of the first simple organisms. Complex volcanic processes and the release of gases from the mantle contributed to the formation of the primary hydrosphere, as vapor condensed and formed the first oceans on Earth. As a result, despite its hostility, this atmosphere acted as a catalyst for the long-awaited changes that allowed Earth to evolve into the planet we know today. The volcanic activity that occurred on Earth during this time was so intense that scientists estimate that, According to some estimates, around 50 million years after the planet's formation, the atmosphere could have been significantly altered. In the early days of Earth, meteorite bombardment occurred with catastrophic intensity. During the first billion years of the planet's existence, starting approximately 4.5 billion years ago, the Earth's surface was subjected to constant impact from cosmic bodies. These bodies ranged from small meteoroids, just a few millimeters in diameter, to massive asteroids as large as entire cities. Studies indicate that numerous collisions occurred during this period. It is estimated that around 100,000 tons of cosmic material fell to Earth each year. As a result, the space above the planet could be imagined as a sky crisscrossed with brilliant trails of falling meteors, as if an artist was waving a brush, leaving trails of light behind. Modern observations show that craters from such impacts can remain on the planet's surface for millions of years, although many of them are eventually eroded or destroyed by volcanic activity. Some craters, like the Chicxulub crater in Mexico, have remained largely unchanged. The Chicxulub crater, incidentally, was formed by an asteroid impact approximately 10 kilometers in diameter, which, according to scientists, may have been responsible for the mass extinction of dinosaurs around 65 million years ago. In the early Earth, craters formed with such frequency and diversity that scientists believe the planet's surface was literally covered with them, creating a lunar landscape where each new impact altered the face of the Earth. This was a time when Earth was under constant cosmic attack, and each collision could bring about catastrophic changes in climate and atmosphere. As a result of this constant impact, many geological processes, such as volcanism and plate tectonics, led to the formation of new mountain ranges and oceans, further complicating the planet's landscape. These events not only shaped the physical structure of Earth, but also created conditions for the emergence of the first forms of life. Thus, meteorite bombardment not only altered the landscape of the Earth's surface, but also played a crucial role in evolutionary processes that eventually led to the diversity of life on the planet. For example, volcanic eruptions triggered by meteorite impacts could release significant volumes of gas into the atmosphere, contributing to the formation of new climatic conditions. Approximately 4 billion years ago, Earth experienced a period known as the Late Heavy Bombardment, during which the number of asteroids falling onto the planet's surface sharply increased. This phase lasted from 100 to 300 million years and was characterized by a continuous flow of large cosmic bodies crashing into the young planet. Estimates suggest that during this time, asteroids the size of contemporary countries like France or Tajikistan fell onto Earth. These collisions were so powerful that they melted the already solidified crust and created enormous craters that can still be seen today. For example, the Bering crater on the Kamchatka Peninsula, with a diameter of about 160 kilometers, was formed by the impact of a large asteroid. During this time, Earth also experienced active volcanic activity, which further exacerbated the planet's conditions. The impacts of asteroids not only created craters, but also released vast amounts of dust and gases into the atmosphere, which then influenced the climate and composition of the atmosphere. Considering that some of these objects could have had diameters of more than 100 kilometers, one can imagine the catastrophic consequences they could have caused. For instance, the impact that occurred around 36 million years ago is considered one of the most significant, when an asteroid about 10 kilometers in diameter caused a mass extinction on Earth. However, during the Late Heavy Bombardment, such giant bodies fell onto the planet constantly. This was a time when Earth felt the full force of the cosmos, and each new impact could change its landscape and chemical composition of the atmosphere. Scientific research shows that it was during this period that the conditions necessary for life began to form, even though life itself was still a distant future. As a result of these impacts, vast oceans and continents were formed, which later became the basis for the development of ecosystems. Important findings, such as meteorites discovered in Antarctica, provide scientists with information about the composition of these ancient asteroids and their influence on Earth. These meteorites contain minerals and organic compounds that can provide insight into how our planet was formed. Additionally, studying chemical elements such as silicon and iron allows scientists to reconstruct the picture of how the interaction with Earth occurred. These phenomena ultimately led to the formation of conditions necessary for the emergence of life. Meteorite bombardment played a crucial role in delivering water to Earth, and this process occurred gradually, creating unique conditions for the formation of our planet's water reserves. Approximately 4 billion years ago, when Earth was just beginning to take shape, the cosmos was filled with icy comets and asteroids rich in water. Comets, consisting of 80% ice, would break apart upon impact with Earth, and their icy cores, turning into water vapor, would form the first clouds in the atmosphere. One of the most famous examples is Halley's Comet, which may have contributed to the formation of Earth's water resources in those distant times. Asteroids containing minerals associated with water also approached our planet and, upon impact, would break apart, releasing precious liquid. Studies show that around 20% of Earth's water may have been delivered by such celestial bodies. In 2018, a group of scientists led by Dr. Christian Kloss from the Institute of Planetary Research in Berlin presented results indicating that analyses of meteorites found in Antarctica contained water ice identical in composition to Earth's water, thus confirming the theory of meteorite bombardment as a source of water. This process did not happen in a single day or year, but spanned millions of years as Earth was continuously subjected to the influence of celestial bodies. Each meteorite, falling on the surface, seemed like a cosmic messenger bringing a drop of life to the young planet. Drop by drop, these impacts formed the future water reserves of Earth, which became the foundation for all forms of life. This gradual process is reminiscent of building a structure. Each brick, each material, is important for creating a solid foundation. The water reserves formed in this way became the basis for the formation of oceans, rivers, and lakes, which in turn provided the necessary environment for the emergence and development of life on Earth. It is important to note that it was meteorite bombardment that created conditions for the formation of an atmosphere capable of retaining water in liquid form, which, in turn, became one of the key factors for the existence of life. As a result of such processes, according to the latest data, around 3 billion years ago, Earth already had a stable level of water, which provided the impetus for the evolution of the first living organisms. The formation of the primary oceans on Earth was not merely a geological process, but a true symphony of nature that lasted for thousands of years. In the early atmosphere of our planet, water vapor was present, formed as a result of volcanic activity and other processes. As Earth began to cool, this vapor gradually condensed, forming droplets of water. Imagine the skies opening up and billions of water droplets raining down, creating continuous streams that did not cease for days, months, or years, but persisted for millennia. These endless rains, like a blessing for the young planet, filled lowlands and depressions in the landscape, gradually forming the first seas and oceans. This process was slow, but inexorable. The cooling Earth led to a surface temperature drop sufficient for water vapor to become liquid. Over this long and complex process, which occurred in conditions far removed from today's, vast water expanses began to appear on the planet's surface. These primary oceans, composed of fresh and saline water, became the foundation for the development of future ecosystems. They not only filled existing depressions, but also catalyzed numerous chemical reactions necessary for the emergence of life. At this stage, as water began to fill the lowlands, the planet was still hot, with surface temperatures sometimes exceeding 200 degrees Celsius, creating unique conditions for further development. Nevertheless, while water filled these lowlands, the atmosphere continued to change, with new elements appearing, ultimately leading to the formation of more stable ecological systems. Over millions of years, this process resulted in the formation of primary oceans that witnessed the first steps of life on Earth. In the early days of Earth, around 3,800,000,000 years ago, the first rains that began to fall were nothing like the ones we imagine today. These were acidic rains, filled with chemical compounds such as sulfuric and carbonic acids, formed as a result of the interaction between volcanic gases and the atmosphere. At that time, the planet's surface was scorching hot, with temperatures exceeding 1,000 degrees Celsius. The water falling from the sky was not pure, as it is today. It contained numerous impurities, making it a threat to any existing life. When these rains poured down on the hot rocks and minerals, they hissed and produced clouds of steam that rose into the air, creating a spectacle that could have astonished even the most seasoned observers. This relentless downpour dictated the conditions on the planet, transforming the charred lands into grey, eroded landscapes where fire and water fought for dominance. Lava flows from the volcanoes met the rainwater, creating explosions and geysers of steam. This contrast between the fiery surface and the acidic rains was not just a natural phenomenon, but a genuine struggle of the elements in which nature sought to find balance. At this stage of Earth's development, the rains played a crucial role in the formation of the first oceans and the establishment of more stable ecosystems. Scientists like Dr. Alan Haley from the University of California claim that these early rains were the catalyst for the formation of the primary water bodies, which later became the habitat for the first simple organisms. These acidic rains, falling on the hot surface, also contributed to the leaching of minerals such as iron and magnesium, creating conditions for future chemical reactions necessary for the emergence of life. Ultimately, this process was not just a random event, but a significant stage in Earth's history, which determined its further evolution. The first bodies of water on early Earth were a remarkable and unstable sight, unlike anything we see today in our oceans. These primordial seas formed around 4 billion years ago, as Earth was just beginning to cool after its formation. The water in these bodies was hot, reaching temperatures up to 100 degrees Celsius, which facilitated active evaporation and the formation of mineral-rich solutions. These seas were murky, often colored in unusual hues due to the presence of various chemical compounds such as iron and copper, creating a striking yet menacing landscape. Imagine water bodies whose surfaces sparkled as if they contained countless precious stones. But in reality, these were microscopic particles suspended in the water, creating a glassy effect. These early seas had no clear boundaries. Their sizes and shapes constantly changed due to ongoing volcanic activity, which produced new rocks and raised land, and due to changes in topography caused by tectonic processes. For instance, when the first continents, such as the Canadian Shield, were forming, the boundaries of these water bodies could contract and expand, leaving behind only traces in the form of sedimentary layers. Continuous volcanic eruptions and tectonic movements could cause new volcanic islands to emerge in these seas, while old ones could sink beneath the waves. These primordial seas also contained a variety of chemical substances, including amino acids and other organic molecules, crucial for the origin of life. Specifically, under such conditions, primary organic matter could form, which could later serve as the basis for the first living organisms. Given that these seas were isolated ecosystems, they could develop unique conditions that facilitated the breakdown and formation of new molecules, ultimately leading to the emergence of life. Consequently, these bodies of water became not just sources of water, but also arenas for chemical reactions that altered the entire history of our planet. In the primary oceans, complex chemical reactions took place that formed the basis for the emergence of life on Earth. These oceans, acting as giant natural laboratories, were filled not only with water, but also with various minerals that came from the Earth's crust. Water actively interacted with these minerals, forming diverse solutions that, in turn, reacted with gases from the atmosphere, such as carbon dioxide and ammonia. This process can be compared to the preparation of a complex dish. Each component adds its unique properties, creating something entirely new. As a result, a kind of chemical broth was formed, in which numerous reactions occurred, providing a variety of chemical compounds. According to scientists' estimates, at that time, thousands of reactions could be happening simultaneously in the oceans, creating ideal conditions for the further development of complex organic molecules. This broth became a place where simple molecules gradually evolved into more complex structures. Research by geochemists like Dr. David Walker shows that it was the combination of water, minerals, and gases that played a critical role in the formation of the first organic compounds. These compounds, in turn, could be predecessors of the molecules that later became the basis for life. The complex chemical processes in the oceans were not random. They followed certain patterns that determined which reactions occurred and in what order. Scientists link these reactions to the primary conditions on Earth that facilitated the formation of complex chemistry necessary for life. For example, in a study published in the journal Nature in 2003, researchers described how high temperatures and pressure at the bottom of the ocean contributed to the formation of organic compounds from inorganic precursors. These discoveries highlight that the primary oceans were not just bodies of water, but active participants in the process of life formation. The extended periods during which these reactions occurred created stable conditions for the accumulation of necessary molecules that could later participate in more complex biochemical processes. Thus, the oceans of that time were not only filled with water, but also with the potential for life, providing a unique environment for the appearance of the first cellular structures. As a result, these chemical processes became one of the key factors that led to subsequent stages in the evolution of living organisms on the planet. Hydrothermal sources on the floor of primary oceans are remarkable oases of heat and chemical activity that played a crucial role in the formation of life on Earth. These unique places, located along oceanic rifts, are the result of the interaction between tectonic plates and magma activity. For instance, in the region of the Mid-Atlantic Ridge, which stretches over more than 3,000 kilometers, scientists have discovered numerous such sources. They release hot water, rich in minerals, from cracks in the ocean floor, creating underwater smokestacks. These smokestacks can reach heights of up to 50 meters and are essentially underwater volcanoes that spew streams of dark, mineral-rich water into the surrounding ocean. The temperature of this water can exceed 300 degrees Celsius, creating a stark contrast with the cold waters of the ocean, which typically range around 2 degrees. The chemical composition of the water released by hydrothermal sources is rich in elements such as hydrogen sulfide, methane, and various metals, including copper and zinc. These conditions create a unique ecosystem where organisms can thrive that use hydrogen sulfide as a source of energy. In such oases of life, such as the tiger and hydra sources, tube worms and bacteria have been found that flourish in conditions where other forms of life cannot survive. These organisms are examples of chemosynthetic ecosystems that function independently of sunlight, relying on chemical reactions for their existence. For example, in 2017, researchers from the Scripps Institution of Oceanography documented a new species of worm that inhabits such extreme conditions and can reach lengths of up to a meter. Hydrothermal sources not only contribute to the formation of unique ecosystems, but are also important for understanding the processes that occurred on early Earth. These places represent a boundary between two worlds: the cold, lifeless water of the ocean and the hot, chemically rich flows emerging from the planet's interior. As a result, hydrothermal sources become not only the subject of scientific study, but also a key element in the search for answers to the origins of life on Earth. The formation of the first continents on Earth began approximately 3.5 billion years ago, when lighter crustal materials began to rise to the surface of the mantle, forming land masses that could be called primary continents. These crustal sections, primarily composed of granite and other light rocks, were small archipelagos that gradually coalesced into larger land masses. At this stage, Earth's history was marked by significant geological upheavals. Active volcanoes spewed lava, creating new islands, and earthquakes shattered the land, altering its contours. For instance, around 2 billion years ago, The locations of today's continents like Africa and South America were mere tiny islands covered in volcanic rocks, devoid of vegetation due to harsh environmental conditions. These young, unstable landmasses constantly changed shape, and their sizes were significantly smaller than today's continents. Volcanic activity was so intense that these islands frequently experienced powerful eruptions, releasing vast quantities of ash and gases into the atmosphere. Archaeologists and geologists, such as Dr. Richard Kerr, assert that it was during this period that conditions began to form for further life development on Earth. At that time, later continents like Gondwana and Laurasia did not yet exist, while the first continents were in constant motion, colliding and breaking apart, leading to the formation of new archipelagos. These events laid the foundation for plate tectonics, which continues to shape our planet today. Notably, archaeological findings in places like Greenland and Australia allow scientists to reconstruct images of these early continents and assess their size, which could have been as small as a few hundred square kilometers. Thus, in the early geological epochs of Earth, there were only small islands that gradually merged into larger land masses, ultimately leading to the formation of today's continents. These primitive formations were true islands of chaos, where each new wave of volcanic activity could completely reshape the landscape in just a few days. In the early Earth, tectonic processes unfolded with unprecedented intensity, creating a dynamic surface that resembled a mosaic of moving elements. The Earth's crust was broken into numerous fragments that constantly shifted under the influence of the planet's internal heat, which was significantly higher than it is today. This heat, emanating from the planet's depths, fueled convective currents in the mantle, driving the movement of the crust. As a result, continents and oceans formed and disappeared, as if they were being created and destroyed by invisible artists. Around 2.5 billion years ago, during the Archean Eon, the first major tectonic events occurred, leading to the formation of the first continents, such as the Craton, which represented a stable part of the Earth's crust. This phenomenon marked the beginning of a long journey in the formation of modern continents. While today, tectonic movements occur slowly, at a rate of only a few centimeters per year. In that period, the speed could reach several meters per year, causing frequent earthquakes and volcanic eruptions. The planet's state was highly variable, and each new eruption could cover extensive territories with a layer of lava, creating new landscapes. 800 million years ago, at the end of the Proterozoic, this process reached its peak with the formation of the first supercontinents, such as Rodinia, which appeared and disappeared over short historical periods, leaving behind only geological traces. This process of crust destruction and formation occurred with such ease as if one were changing tiles on the floor. As a result, the Earth's surface was not only subject to constant changes, but also served as a testament to an endless cycle of creation and destruction, which shaped the conditions for life as we know it today. With each new shift of the crust, with each new wave-like movement, the planet's surface changed, like a canvas under an artist's brush, leaving us only fragments of history. Subduction is one of the most remarkable processes in geology, where one tectonic plate slowly descends beneath another. Imagine an oceanic plate, such as the Nazca Plate, the size of an entire country, slowly moving eastward and colliding with the continental plate of South America. This process does not happen instantaneously. The rate of subduction can be as slow as a few centimeters per year. Over millions of years, this slow but relentless process shapes the landscape, altering the relief, creating mountain ranges, and causing earthquakes. As the plate descends, it passes through different layers of the mantle, where temperature and pressure rise sharply. This creates conditions for partial melting, resulting in the formation of magma chambers that can lead to volcanic activity. For example, the Andes volcanoes, which were formed as a result of subduction, are a direct consequence of this process. The Cotopaxi volcano in Ecuador, one of the most active volcanoes in the world, periodically erupts, reminding us of the power hidden beneath the Earth's crust. Like a giant conveyor belt that returns surface material back into the planet's interior, subduction demonstrates how land and oceans are interconnected, with each plate being part of this endless system. It is important to note that in places where subduction occurs, such as the western coast of South America, the strongest earthquakes in the world are observed. 80% of all earthquakes occur in subduction zones, where plates get stuck against each other, accumulating tension until it is released. An example of such an earthquake is the catastrophic earthquake in Chile in 1960, which had a magnitude of 9 and was one of the strongest in history. This process also leads to the formation of deep oceanic trenches, such as the Mariana Trench, which reaches a depth of 11 kilometers. Here, at the bottom of the ocean, there is also continuous movement that ultimately shapes and changes the geological landscape of the Earth. Subduction is not just a process. It is an entire system in which the mantle and crust constantly interact, creating conditions for life on the surface. In the early history of Earth, around 2 billion years ago, the process of forming the first mountain ranges began, a result of the collision of tectonic plates. This was not an instantaneous event. Collisions occurred over millions of years, causing sections of the Earth's crust to slowly fold and rise, creating mountain ranges. The planet's surface at that time was vastly different. There were no modern rivers or glaciers to erode these young formations. Instead, wind and rain gradually smoothed the sharp peaks of the newly raised rocks. These mountains, pushed up from the Earth, were not the majestic peaks we see today, but rather low, sharp ridges bordered by dark volcanic rock. Volcanic activity was quite common, and formations like basalt plates resulted from eruptions. Later, as the crust cooled, intrusive rocks like granite also contributed to shaping the landscape. These processes occurred against the backdrop of active volcanic activity characteristic of the time when Earth was young and full of energy. For example, in the region of the modern Appalachians, which began to form around 400 million years ago, geologists assert that the initial mountains were significantly lower and much more rounded than they are now. They were the result of the collision of ancient continents such as Laurussia and Gondwana, which formed the first complex mountain structure. These mountain-forming processes occurred in the context of high temperatures and pressures, which facilitated the metamorphism of mountain rocks. One of the most famous examples of such processes is the formation of the Ural mountain range, where the collision of plates began around 300 million years ago and continued for millions of years. At this stage of formation, when the mountains were just beginning to rise, they were not yet as tall and grand as they are today. Their height was significantly lower, and they looked like small hills, scarred by cracks and fissures. Since erosion had not yet fully altered their appearance, we can imagine them slowly growing, emerging from the Earth due to the relentless pressure of tectonic processes. Time is merciless, and only the wind, sweeping between the sharp edges of these newborn peaks, reminds us of the true battle of nature's forces that once took place here. These early mountain ranges became important geological structures that would shape the climate, ecosystems, and even the cultures of people who would live on their slopes in the future. It is worth noting that at that time, there was not such a developed ecosystem as today. Life was just beginning to develop, and each new mountain range created unique conditions for the appearance of new forms of life. For example, in the same region of the Appalachians, where there are many coal deposits, the mountains served not only as natural barriers, but also determined the climatic conditions for the surrounding territories, promoting the development of forests and diverse flora. The process of altering Earth's early atmosphere was long and complex, spanning hundreds of millions of years, and can be visualized as a planetary breath that slowly and deeply transformed the environment. Initially, the atmosphere, formed around 14 billion years ago, was dense and toxic, preventing light from reaching the surface. Over time, beginning with the Archean period, geological processes such as volcanic activity started to introduce changes. Volcanoes emitted gases that gradually diluted the initial composition of the atmosphere, creating conditions for more complex chemical reactions. Approximately 3.5 billion years ago, the interaction between the atmosphere and oceans led to the formation of the first simple life forms, such as cyanobacteria. These microorganisms, in turn, contributed to the production of oxygen through photosynthesis, gradually increasing its concentration in the atmosphere. Gradually, the sky became lighter, transitioning from dull grey hues to blue, and the density of the atmosphere decreased, allowing sunlight to penetrate deeper into the oceans and onto the land. This process was not only chemical, but also physical, as temperature and pressure changed, influencing climate conditions. With each million years, the atmosphere became less toxic and more suitable for life, creating conditions for the appearance of new biological organisms. Thus, over 2 billion years, from the Archean to the Proterozoic period, the atmosphere underwent significant changes that made possible the existence of complex ecosystems. The first mass extinction of organisms, which occurred around 250 million years ago, marked a turning point that again altered the composition of the atmosphere. But this was just a part of the long and complex path to the creation of the modern balance. By the end of the Paleozoic era, the atmosphere had acquired a more balanced composition, which facilitated further development of life on Earth. The process of weathering is a key factor that has significantly altered the composition of Earth's atmosphere. Each time rain falls on the surface of rock, it enters into complex chemical reactions that can be compared to a slow dance between water, rock, and air. Water, containing carbon dioxide and acids, dissolves minerals in rocks such as granite and limestone. For example, in limestone areas, rain can dissolve calcium carbonate, forming bicarbonate of calcium, which then moves into rivers and oceans. This process, occurring over millions of years, leads to changes in the chemical composition of both rocks and the atmosphere. An important aspect of this process is the leaching of potassium, sodium, and magnesium, which become available to plants and other living organisms. As a result, when rain interacts with rocks, it not only changes the physical structure of the Earth, but also contributes to an increase in the oxygen content of the atmosphere. For instance, in the Appalachian region, where sedimentary rocks predominate, weathering leads to the formation of clays and loess, which enrich the soil. These changes occur wherever water comes into contact with rock, creating a global geochemical cycle that supports life on the planet. According to geochemists like Dr. Laura Randall, weathering is the primary process that maintains the balance between atmospheric gases and the biosphere. It is important to note that the changes brought about by weathering do not occur only in the tropics, where high humidity accelerates the process, but also in drier regions, where rain may be infrequent but still plays a role in altering the chemical composition of soil and the atmosphere. In arid regions, rock weathering occurs more slowly, but still creates conditions for the formation of sandstones and other sedimentary forms. This process, observable in practice, illustrates how even the smallest drops of water can, over time, dramatically alter the appearance of the planet by interacting with minerals and elements that make up its crust. At the boundary of the Archean and Proterozoic eras, approximately 2.5 billion years ago, a pivotal event occurred that was crucial for the formation of Earth's atmosphere. The primary ozone layer began to form. Solar radiation penetrating the upper layers of the atmosphere initiated photochemical reactions, resulting in the active interaction of oxygen molecules produced during photosynthesis with ultraviolet light. These interactions led to the breakdown of oxygen molecules into atoms, which then combined with other oxygen atoms to form ozone molecules. During this period, when the planet was not yet protected from harmful cosmic radiation, an invisible shield began to form high above Earth's surface. This ozone layer acted as a barrier, blocking a significant portion of ultraviolet radiation and thus protecting living organisms from its destructive effects. The importance of this process for the future development of life on Earth is difficult to overestimate, as it created more favorable conditions for the evolution of organisms, allowing them to move onto land and adapt to new conditions. The formation of the ozone layer was not just a physical phenomenon, it was a qualitative leap that determined the further fate of the biosphere. During the formation of this layer, various molecules interacted with each other, creating more complex structures that became the basis for further chemical evolution. With each million years, the ozone layer became denser, and by the end of the Proterozoic era, it reached significant thickness, allowing life on Earth to develop and diversify. This invisible shield, which we perceive as a given, became one of the most important factors contributing to the emergence and maintenance of life on the planet. Major research conducted in the 20th century confirmed that without this layer, life as we know it would be impossible. Astronomers and geologists such as Dr. John Kerr conducted numerous studies to determine how the ozone layer formed and how its absence could have affected the existence of the first living organisms on Earth. For example, data from geological layers show that before the formation of the ozone layer, the level of ultraviolet radiation was tens of times higher than now, making the planet's surface practically unsuitable for life. Preserved fossilized remains, such as stromatolites, serve as evidence of how life adapted to these changing conditions. This process of forming the ozone layer became one of the most significant events in Earth's history, opening new horizons for life and contributing to its diversity and complex development. In the primordial oceans of Earth, where chaos reigned, a unique process began that can be likened to a chemical dance, in which simple molecules combined to create more complex structures. This occurred around 4 billion years ago, when life had not yet appeared on the planet, but the conditions were beginning to form for its emergence. Energy from lightning and ultraviolet radiation penetrating the atmosphere catalyzed reactions, leading to the formation of new compounds. These molecules, which at the time might have seemed insignificant, began to interact with each other, forming chains that over time became increasingly complex and organized. Over millions of years, in conditions of high temperatures and pressure, constant collisions and reactions occurred, resulting in the emergence of the first organic structures. This was an era when molecules, like dancers, exchanged partnerships, forming new bonds and structures that eventually became the foundation for the formation of the first simplest forms of life. These molecules, including derivatives of atmospheric gases entering the ocean, found each other in this primordial soup, creating something far more complex than themselves. Scientists such as Stanley Miller in 1953 demonstrated that under conditions mimicking early Earth, it was possible to obtain organic compounds such as amino acids, which confirms the possibility of life arising under such conditions. Lightning energy, as experiments have shown, could lead to the formation of these molecules, creating conditions for their further combination and evolution. In this process, thermal sources undoubtedly played a role, emitting heat and providing the necessary environment for reactions. Thus, in the primary oceans, a true chemical spectacle unfolded, where from simple components, more complex structures emerged, which became the basis for the appearance of life on Earth. In this context, it is important to note that precisely these molecules, with their unique properties, became the basis for the formation of the first cells, which, over billions of years, evolved into multicellular organisms. The RNA world hypothesis is one of the most intriguing concepts in prebiotic evolution, proposing that RNA molecules could have been the precursors to the first living organisms. RNA, or ribonucleic acid, possesses a unique ability to simultaneously store genetic information and catalyze chemical reactions, making it the ideal candidate for the role of the primary element in the origin of life. The first idea associated with this hypothesis was proposed in 1962 by Francis Crick and his colleagues, suggesting that RNA could perform functions similar to both DNA and proteins. These molecules could have functioned as simple systems that not only responded to their environment, but also adapted to it, marking an important step towards the development of more complex forms of life. RNA, as molecules capable of self-replication, would have provided the first forms of chemical evolution, where chemical reactions and their outcomes became the basis for the emergence of new structures. Since RNA molecules can form various structures, such as virions, they could have interacted with their environment, extracting necessary substances for their existence and reproduction. This creates the image of the first candidates for the role of living beings, balancing on the border between non-living and living matter. An important aspect is that this process was not random, but the result of a prolonged chemical evolution in which RNA molecules developed and adapted in the conditions of early Earth. Scientists like Jack Szostak conducted experiments demonstrating that RNA molecules can spontaneously form under conditions mimicking early Earth, thus confirming their natural origin. This opens new horizons in understanding how life could have emerged and highlights the complex mechanisms that could have governed this process. For example, in 1991, Szostak and his colleagues showed that simple RNA molecules can catalyze reactions, adding another layer of complexity to the view of RNA as a precursor to life. Thus, RNA could have become the main element linking non-living nature with living systems, opening new perspectives in the study of the origin of life on Earth. Research conducted over the past decades has shown that RNA molecules can perform a wide range of functions, including the regulation and control of biochemical processes, further confirming their key role in evolution. The formation of the first cellular membranes was a pivotal moment in the history of life on Earth. Lipid molecules in an aqueous environment have two distinct parts: hydrophobic, water-repelling, and hydrophilic, water-attracting. This unique structure allows them to spontaneously arrange into double layers, forming thin films that can be considered the first cellular membranes. This process, occurring around 3.5 billion years ago, laid the foundation for the creation of microscopic vesicles known as liposomes. Water, being a universal solvent, causes the hydrophobic tails of the molecules to hide inside, while the hydrophilic heads face outward, forming protective shells. These incredibly thin membranes created isolated spaces where more complex chemical reactions could occur. Without such separation, it is difficult to imagine the development of life, as it allowed the organism to protect its internal contents from the external environment and regulate the exchange of substances. Liposomes, composed of phospholipids, served not only as a physical barrier, but also as a platform for further biochemical processes, such as protein synthesis. These membranes were the precursors of the cells we observe today. Research conducted at the end of the 20th century showed that such structures can spontaneously form in laboratory conditions, indicating their natural origin on early Earth. A crucial aspect of this process is that the formation of membranes contributed to the creation of specialized microenvironments where the precursors of living organisms could develop. These primary membranes provided conditions for the emergence of metabolism and, consequently, for evolution. The formation of cellular membranes from lipids became the basis for all living cells known today. Every cell, whether a bacterium or a complex multicellular organism, has such a membrane that protects it from external influences and allows it to exchange substances with the surrounding environment. This protection and isolation of molecules became essential conditions for the emergence of life on our planet. The study of the emergence of the first protocells is an engaging process that spans billions of years, beginning with the formation of Earth around 4 billion years ago. During this period, molecules formed as a result of chemical reactions began to interact with each other, creating complex systems. Approximately 3.5 billion years ago, in the oceans of our planet filled with organic compounds, a process began that can be characterized as a barely audible whisper, gradually transforming into a symphony of life. This symphony consisted of molecular systems that began to acquire properties characteristic of living organisms, such as self-reproduction and metabolism. These molecules, composed of carbon, hydrogen, oxygen, and other elements, could form more complex structures due to chemical reactions occurring in conditions reminiscent of modern hydrothermal vents. In such conditions, high temperatures and pressure favored the formation of the first organic compounds, which became the foundation for further life development. For example, the renowned scientist Stanley Miller conducted an experiment in 1953, in which he created amino acids necessary for life using simple chemical substances and electrical discharges, mimicking conditions on early Earth. Gradually, molecules began to form more complex systems that could interact with the surrounding environment, responding to temperature and chemical composition changes, indicating the first step towards the evolution of living organisms. This interaction between molecules became the basis for metabolism, where molecules absorbed nutrients and released waste, a crucial aspect of any living system. This process was slow and gradual, and the boundary between the non-living and the living became increasingly blurred. An example of such gradualness is the formation of membranes, which provided isolation and protection, but also allowed molecules to exchange substances with the surrounding environment. These membranes, although not fully developed cellular structures, began to perform functions necessary for sustaining life. Over time, molecules such as RNA began to exhibit the ability to self-replicate, which became a key moment in the evolution of the first protocells. Research shows that these molecules could not only copy themselves, but also change, adapting to changing environmental conditions. Simultaneously, the simplest metabolic pathways were formed, allowing these molecular systems to absorb and convert energy from the surrounding environment, further blurring the boundaries between the non-living and the living. In this context, it is important to note that the process of the emergence of the first protocells was not instantaneous, but represented a long evolution, in which each step was the result of a complex network of chemical interactions. Ultimately, such an approach to understanding the origin of life allows us to better comprehend how a complex system capable of self-reproduction and adaptation could arise from the chaos of simple molecules. As a result, in oceans filled with chemical reactions, life emerged, which later led to the appearance of the incredible diversity of organisms that we observe today. Stromatolites are the oldest known evidence of microbial life on Earth and represent unique layered structures formed by the activity of cyanobacteria and other microorganisms in shallow seas. These structures can be considered the first ecosystems on the planet, where microorganisms coexisted in close interaction. They were formed through the precipitation of calcium carbonate, which cyanobacteria released during photosynthesis. Stromatolites are small mounds growing on the floor of primary oceans and typically reach heights from several centimeters to several meters. The oldest known stromatolite samples were found in Australia, in the Fortescue Formation, and are dated to approximately 3.5 billion years ago. This indicates that microbial life appeared on Earth at very early stages of its formation. Stromatolites grow incredibly slowly, sometimes by only a few millimeters per year, making them true living fossils. They continue to exist today, and the most famous modern stromatolites can be seen in the lagoons of the Bahamas and Australia, where they continue to play their ecological role. In these ancient structures, one can observe a layered texture resembling a multi-layered cake, where each layer is the result of the interaction of microorganisms with the surrounding environment. These layered formations serve not only as indicators of ancient ecosystems, but also as important sources of information about climatic conditions and the chemical composition of oceans in various geological epochs. For example, the analysis of the chemical composition of stromatolites from the Aptian Formation in New Zealand showed that the level of oxygen in the atmosphere was significantly lower during the time they formed. Thus, stromatolites are not only evidence of ancient life, but also important markers for understanding the evolution of the atmosphere and oceans on our planet. Research on stromatolites has been conducted by many renowned scientists, such as Dr. David Lipps, who published works on the significance of stromatolites in the study of early forms of life in 2005. Stromatolites continue to attract the interest of scientists because their study can shed light on the emergence of life on other planets, such as Mars, where conditions could have been similar to those on early Earth. They are key elements in the study of not only biology, but also geology, as their layered structure reflects changes in the conditions of the surrounding environment and climate over billions of years. The process of photosynthesis in ancient cyanobacteria, which emerged around 3 billion years ago, was a true revolution in the biosphere of Earth. These microscopic organisms, measuring only a few micrometers, began using solar energy to synthesize organic compounds from carbon dioxide and water. Photosynthetic cyanobacteria, such as Synechococcus and Prochlorococcus, use chlorophyll and other pigments to capture sunlight. During photosynthesis, they convert light energy into chemical energy, releasing oxygen into the atmosphere as a byproduct. This event, known as the Great Oxidation, occurred around 2.5 billion years ago and led to a radical change in the chemical composition of Earth's atmosphere. Before this, the atmosphere was primarily composed of methane and ammonia, but after the appearance of cyanobacteria, the oxygen level began to rise rapidly. Oxygen, initially dissolving in the oceans, soon filled the atmosphere, providing a boost to the evolution of aerobic organisms. Thus, cyanobacteria not only survived, but also actively altered the conditions of their habitat, creating favorable conditions for the life of more complex organisms. Over millions of years, these microorganisms, spreading across the planet, formed the basis for all subsequent ecosystems. Their photosynthetic processes not only changed the atmosphere, but also influenced the climate, contributing to the formation of the ozone layer, which protects living organisms from harmful ultraviolet radiation. As a result, thanks to these tiny creatures, life on Earth was able to evolve into diverse forms, ranging from simple single-celled organisms to complex multicellular organisms. Scientists such as biochemist and molecular biologist Dr. Christopher Kaminski emphasized that the photosynthesis of cyanobacteria became the foundation for the formation of the biosphere as we know it. These organisms not only provided oxygen to the atmosphere, but also became the primary source of food for many other living beings. The importance of cyanobacteria in ecosystems cannot be overstated. They participate in biogeochemical cycles, fixing carbon and nitrogen, which helps maintain balance in nature. Microscopic cyanobacteria, which we cannot see with the naked eye, have had a colossal impact on life on Earth, and their photosynthetic activity continues to influence the atmosphere and climate of our planet. Over the course of millions of years, photosynthetic organisms, such as cyanobacteria, began to release oxygen into Earth's atmosphere. This process, which can be imagined as a gradual and unnoticed transformation of the planet, changed not only the color of the sky, but also the composition of the oceans, filling them with a new chemical element. Initially, when oxygen was just beginning to accumulate, the atmosphere was akin to a desert, where anaerobic organisms reigned, unaware of what it meant to breathe oxygen. With each passing year and each wave of photosynthetic activity, the sky became increasingly blue, and the oceans became more saturated with new substances, creating conditions that could support life as we know it. However, this process was not benign. Oxygen, being toxic to most of the life forms that existed at the time, became the cause of mass extinctions. Many organisms that had evolved for millions of years in an oxygen-free environment could not adapt to the new conditions and perished. However, it was precisely this toxic element that opened up new evolutionary horizons for those who survived. Thanks to oxygen, new groups of organisms, such as multicellular algae and subsequently animals, were able to develop and adapt to diverse environmental conditions. Oxygen became the basis for complex metabolic processes, allowing living beings to effectively use the energy obtained from food. This change led to the diversity of life forms and paved the way for the emergence of complex ecosystems. Thus, as a result of the Great Oxygen Event, Earth not only changed its appearance, but also laid the foundations for future evolution. Ultimately, this transformation became one of the most significant moments in the history of our planet. Oxygen, which was once deadly to the ancient inhabitants of Earth, is now an essential element for the existence of those who came later. With its help, complex life systems have developed that continue to exist to this day, including us, humans. Red-banded iron formations are unique geological formations that serve as evidence of the oxygenation of oceans that occurred around 2.5 billion years ago, during the period known as the oxygen catastrophe. These rocks consist of alternating layers rich in iron and silica, forming striking bands that seem to tell the story of the process where dissolved iron in seawater reacted with oxygen, forming oxides and precipitating as sediment. A crucial role in this process was played by microorganisms such as cyanobacteria, which began to photosynthesize, releasing oxygen into the atmosphere and oceans. This oxygen accumulated and, upon contact with dissolved iron, led to the formation of iron oxides that then settled to the bottom of the ocean. An example of such formations can be found in the layers of iron formations discovered in places like the Gauteng Formation in South Africa, where layers can reach a thickness of several hundred meters. These rocks are not just geological formations, they are a record written in stone that reflects one of the most significant moments in Earth's history. Each layer of red iron formation is an archive that preserves information about chemical and climatic changes that occurred on the planet, as well as how life began to adapt to new conditions. With the help of such layers, geologists and paleontologists can reconstruct the picture of ancient oceans and climate, which allows for a better understanding of how our planet has evolved over millions of years. In particular, similar formations have been found in Russia on the Ural Mountains, which date back to the same periods as the South African ones and provide an opportunity to study how oxygenation affected the global ecosystem. The iron formations formed under conditions of low temperature and pressure indicate that the process of their formation was slow and continuous, which is confirmed by various dating methods, including radiometric studies. These rocks are not only evidence of ancient oceans, but also an important indicator of changes in the biosphere when life began to actively influence the composition of the atmosphere and hydrosphere, which in turn became the basis for the further evolution of complex forms of life, including the first multicellular organisms. The snowball Earth hypothesis suggests that around 800 million years ago, our planet could have been almost entirely covered in ice. This period is known as the Neoproterozoic and is characterized by the possibility that the surface temperature of Earth could have dropped to critical levels, turning the oceans into frozen deserts. The causes of this global cooling are linked to changes in the composition of the atmosphere, particularly a sharp decrease in the concentration of carbon dioxide, which plays a key role in the greenhouse effect. As a result of this cooling, the temperature on the equator could have dropped to -40 degrees Celsius, making life on the planet extremely difficult. Visualizing this epoch, one can imagine Earth encased in an ice shell, with rare oases of open water forming around volcanic islands. These islands, due to their active volcanoes, created local warm conditions that allowed some forms of life to survive in this hostile environment. However, conditions were so harsh that only the most adapted organisms could exist in such conditions. Research indicates that it was during this period that the selection of the most resilient forms of life took place, laying the foundation for further evolution. For example, in the mountains of Tasmania, fossils dating back to this time have been found, indicating the existence of simple organisms such as microscopic algae and bacteria that could survive in conditions of constant cold and light deprivation. These organisms formed the basis for more complex ecosystems that began to develop as the climate became milder. Thus, despite the harsh conditions, the snowball Earth epoch played a crucial role in shaping the biosphere by selecting organisms that could subsequently adapt to changing conditions. It is important to note that the snowball Earth hypothesis is still actively debated among scientists, and many researchers, such as Dr. David Levering from the University of Leicester, continue to study geological data to better understand the climate changes of that time. A deeper understanding of these processes can help us not only understand our history, but also predict how climate changes may affect life on Earth in the future. Approximately 2 billion years ago, the first eukaryotic cells appeared and became a true breakthrough in the evolution of life on Earth. These cells, with their complex organization, resembled miniature cities where each organelle performed a unique function, like a separate district in a metropolis. Unlike prokaryotic cells, eukaryotes had a nucleus that protected their genetic material, and numerous organelles such as mitochondria and chloroplasts that provided the cell with energy and enabled it to perform photosynthesis. This level of organization allowed cells to develop and adapt to various environmental conditions. For instance, mitochondria, as they evolved, became the primary source of energy for cells, converting chemical energy into a form that could be utilized. This step paved the way for multicellularity, as cells began to unite into complex organisms capable of performing more complex functions and interacting with one another. As a result, when these first eukaryotes began to appear in the aquatic environment, they laid the foundation for the formation of all modern forms of life, including plants, animals, and fungi. A key feature of eukaryotic cells is their ability to exchange genetic material, which allows them to evolve faster and adapt to new conditions. This, in turn, facilitated the emergence of evolutionary innovations. For example, the appearance of multicellular organisms occurred because cells began to specialize in performing specific functions, enabling the existence of more complex forms of life. Thus, the first multicellular organisms appeared around 600 million years ago and became the precursors of all modern animals. Eukaryotic cells became a pivotal moment in the history of life on Earth, opening the way to the diversity of forms and ecosystems that we observe today. The discovery of the first eukaryotes became possible thanks to the work of many scientists, such as Lynn Margulis, who proposed the theory of symbiotic evolution, explaining how cells could unite and develop together, forming more complex structures. These cells became the foundation for the further development of all living organisms, and their diversity became the basis of the biosphere in which we live. The theory of endosymbiosis, proposed by Lynn Margulis in the mid-20th century, suggests that some organelles of eukaryotic cells, such as mitochondria and chloroplasts, originated from engulfed bacteria. During evolution, one cell could engulf another, but instead of digesting it, as happens in normal digestion, it established mutually beneficial relationships. For example, the ancestors of modern mitochondria were likely free-living aerobic bacteria that provided their host with ATP, molecules essential for energy production. In return, the engulfed cell received protection from the external environment and access to nutrients. This process can be compared to a mutually beneficial deal where both parties benefit. Such unions may have occurred repeatedly over millions of years, leading to the formation of more complex cellular structures. For instance, in some plant cells, chloroplasts, which have the ability to perform photosynthesis, originated from cyanobacteria that, upon entering the cell, began to produce glucose while their hosts provided them with the necessary conditions for life. This process illustrates how once competitive organisms became parts of a single whole, significantly expanding their functional capabilities. Research indicates that such symbiotic relationships could have been the foundation for the further evolution of complex organisms. For example, such symbioses led to changes in metabolism that allowed cells to efficiently use oxygen, which in turn led to the emergence of multicellular organisms. Interestingly, modern research on the genetic material of mitochondria shows that their DNA differs from the nuclear DNA of the cell, which serves as evidence of their bacterial origin. These discoveries underscore that the process of endosymbiosis is not only key to understanding cellular evolution, but also demonstrates how life on Earth developed through cooperation. Scientists continue to study how such symbiotic relationships can form in modern organisms, which may provide insights into the evolution of life on our planet. It is worth noting that not all such symbioses were stable, and many ancient unions may have disappeared, but those that survived led to the formation of new forms of life. The first multicellular organisms appeared around 800 million years ago, when individual cells began to unite into simple colonies. These colonies were something intermediate between plants and animals, floating in ancient seas rich in nutrients. Multicellular organisms, such as algae, were neither completely plant-like nor completely animal-like, but rather something new that emerged from a unique symbiotic relationship. An important aspect of their existence was that each cell in the colony performed a specialized function, allowing the organism to function more efficiently. For example, one group of cells could engage in photosynthesis, while another was responsible for movement and protection from predators. These primitive creatures were remarkably simple compared to modern forms of life, but their emergence was a revolutionary step in evolution, allowing nature to experiment with new forms of life organization. The process of cell aggregation led to a true evolutionary revolution. The appearance of multicellularity opened the door to complex forms of life that we observe today. Scientists such as biologist David Taylor assert that these early multicellular organisms were the precursors of all modern animals and plants. During their existence, they could reach sizes of several centimeters, which was a significant achievement for their time. These organisms did not have a nervous system or complex organs, but their simplicity was compensated for by the efficiency of cell interaction. For example, in simple algae colonies, cells could exchange substances through direct contacts, ensuring their survival in the challenging conditions of the ancient ocean. Such colonies, consisting of hundreds and even thousands of cells, could form structures reminiscent of modern coral colonies. This step forward in evolution became the basis for the appearance of more complex multicellular organisms, such as sponges and flatworms, which appeared significantly later, around 500 million years ago. Early multicellular organisms were a crucial stage in the development of life on Earth, as evidenced by findings such as fossil traces discovered in the Ediacaran Formation, which date back to approximately 600 million years ago. These traces show that on Earth there already existed organisms with diverse morphology and capabilities. The Ediacaran biota represents some of the oldest known multicellular organisms on Earth. These creatures, which existed approximately 600 million years ago, were vastly different from anything we see today. Their bodies were flat and soft, resembling leaves or feathers, making them extremely difficult to classify according to modern standards. For instance, organisms like Dickinsonia could reach lengths of up to a meter and had shapes reminiscent of large leaves that gently swayed in marine currents. Unlike the rigid skeletons and predatory forms of life we are accustomed to, the Ediacaran organisms lived in a world without predators. This was a time when life on Earth was just beginning to explore multicellular forms, and the Ediacaran biota served as a vivid example of this process. In oceans filled with soft sediments, their strange forms, seemingly straight out of a science fiction novel, moved smoothly, leaving traces on the seabed that we now study. These organisms seemed to belong to another reality, alien to our familiar ecosystems. They exhibited a diversity of forms and structures, from peculiar ones resembling jellyfish to more complex forms like Chaniodiscus, which had stalks attached to the seabed. Since the Ediacaran biota existed before the appearance of hard skeletons, such organisms as cloud jellyfish did not create the familiar ecosystems based on food chains and predation. They simply existed, absorbing nutrients from the water, and their way of life was completely unlike anything we can observe today. This period was not only an evolutionary experiment, but also a prototype for the future ecosystems that later filled the oceans and land. The absence of hard structures makes the study of Ediacaran organisms challenging and has sparked debates among scientists about their classification and significance. One such researcher was David Greff, who in his work in 2005 described the importance of these organisms in the context of the evolution of multicellular life. It was during this period that we began to see how life on Earth was rapidly changing, paving the way for the emergence of more complex organisms. The Ediacaran biota became a key to understanding how the first multicellular organisms might have looked and how they were connected to later forms of life. This deep biology leaves many questions, particularly regarding their origin and extinction, making their study not only intriguing, but also necessary for understanding the evolutionary history of our planet. Scientists continue to discover new species and investigate existing ones, and each new discovery, as a rule, brings more questions than answers. In the end, It is precisely this that makes the Ediacaran biota so captivating for study. In 2030, a new form was discovered in Australia that could shed light on the last mysteries of this ancient epoch. The transformation of Earth's appearance over billions of years is a remarkable journey that deserves our attention. Imagine our planet at the beginning of its existence as a fiery sphere, surrounded by toxic gases and volcanic activity. It has endured incredible catastrophes, such as meteorite impacts that formed the lunar crater, and epochs when water filled its depressions, turning them into oceans teeming with mysteries. Then, during ice ages, when vast masses of ice-covered continents, Earth gradually but surely changed its appearance and climate, creating suitable conditions for life. These conditions, like streams of water bending light, led to an infinite variety of organisms, from simple single-celled forms to complex multicellular beings. The uniqueness of this path is undeniable. Each step Earth took was necessary to ultimately form the ecosystems we know today. However, the result of this colossal process is incredibly fragile. The modern conditions of life we take for granted depend on the balance and interaction of numerous factors, from climate to ecology. The fact that we can study this history while lying in our beds underscores the value of our planet. It is not just our home. It is the result of billions of years of evolution, catastrophes, and triumphs. And when we close our eyes and drift off to sleep, we have the opportunity to dream of ancient seas where life was just beginning its journey and the first glimpses of existence on young Earth. Each star in the sky can remind us that we are not alone in this vast cosmos, and that our history is just one of an infinite series of stories waiting to be discovered.